All right, good day, everyone. What we're going to be doing in this video is quickly going over just transformations of reciprocal graphs, okay? The main idea of this is just kind of going over a basic understanding of what those reciprocals do, and obviously within class tomorrow, we'll go kind of more in depth on these particular values, okay? So here's the first key thing I want you to understand. Truthfully, how you're going to affect these graphs is almost going to be the same way we would affect a sine or a cosine graph, okay? The idea remains the same, that we're going to be moving left, right, up, down. We're going to have period and amplitude changes, things like that. Okay. The big thing I want you to understand is that the same way you would affect a sine or a cosine graph, you're going to be affecting a cosecant, a secant, a tangent, or even a cotangent graph. Okay. So with that being said, we need to have a basic understanding of what cosecant really is. Well, cosecant is the opposite of a sine graph. So once again, we have to understand how to graph out just a basic cosecant function. Well, wherever sine is at 0, that would be considered an asymptote in our cosecant graph. So sine starts at 0, sine is 0 at pi, and sine is 0 at 2 pi. Okay? Those would create our three asymptotes, allowing me to graph out the original cosecant graph, which looks similar to this. At +1, it goes up. -1, it goes down. Okay? Now, understand, truthfully, how we're actually going to affect this graph based off the transformations given is almost the same way we would affect a sine graph. Okay? If I was given a -2 sine of x, this would be both a reflection and it would be an amplitude of 2, which would really just affect my max and my min. Well, the same way that this is affected, your cosecant graph is also going to be affected. If this is the original cosecant right now, -2 cosecant of x would just be the same way would just be affected the same way as a sine would. This is a reflection, and you have an amplitude of, I do not know why that thing's going away from me. Amplitude of 2. So truthfully, think about what is affected in amplitude. Whenever we had an amplitude change, that would affect my max and my min. Well, even though the graph looks different, you still have a max and a min here. So these are both going to be pressed up to a value of 2. Okay? The only other difference now is that we have a reflection also involved in here. So both of these graphs need to be flipped into the other region. So literally, I'm going to take the graph given to me and apply that. Technically, I would have a new graph down here and a new graph built up here. Giving me a new graph, if I erase the old one, that looks similar to this. This graph in red is -2 cosecant of x. Okay? Notice how I just took the original and I applied those two transformations. The amplitude affected the max and the min. The reflection flipped both of those values. The other interesting thing is if I were to actually graph out -2 sine of x, it would look similar to this. -2 sine of x would start at 0. It would go down to -2, come back up to 0, go up to 2, come back down to 0. So notice how it's really just a reciprocal of the original graph itself. So you could necessarily graph out the sine function and then just build cosecant off of that if you'd like. Okay? The transformations in itself is kind of the same either way. It's affecting the graph the same way that we could almost look and see both graphs within it. Okay? But understand that's kind of the first key thing. One of the things you're also going to bring up is that we have to have a basic understanding of the original graphs. We have to be able to look at a graph and say, I know what that graph looks like, okay? If you can go into a problem knowing what cosecant looks like and how it is affected, then graphing out is going to be that much easier. Next, if we look at something like the cotangent of x minus pi over 4, well, the key thing I want you to understand is anytime we're moving a left or right transformation, we want to move the things that are easily movable. Okay, and those things truly are your asymptotes and your x-intercepts. So if I look at this problem and I see it's going by right pi over 4, truthfully, all I'm going to do with all of these set points is move it by pi over 4. So I'm going to take this asymptote and move it to this location, which is about pi over 4 to the right over. I'm going to take this coordinate, this x-intercept, and move it right by pi over 4. Okay? Then I'm going to take, oops, I didn't need to make an asymptote there. That was just a coordinate. Let me redo that. Move this coordinate by right by pi over 4. Same thing one more time. I'm going to take this value and move it by right pi over 4. So see, all I'm doing is I'm finding spots that are easily movable. I can move asymptotes. I can move x-intercepts. Don't really focus on the line. Focus on the values that you know are there. Okay? Now, if I actually make this clean and actually erase the things that I really don't need anymore, I move that line. I move that dot to the new position. And just by shifting everything to the right, notice what that does to my graph. It's literally the same exact picture, just shifted a little bit to the right. Okay? And I can apply that even to the rest of this. If I shifted these values over here by right pi over 4, it would simply be just shifting this coordinate to the right by pi over 4 and creating that picture with an asymptote that's off the screen, off to the right over here. Okay? So when you're shifting things and when you're changing periods or any of that, focus on the values that are easily movable. Okay, asymptotes, x-intercepts. If we can move those values, then your life will be a lot easier when you're doing these problems. Okay. The last thing that we really want to talk about is a vertical translation. How do we affect a vertical translation? Well, hopefully this is one of them that are actually going to come out to be the easiest of the bunch. Okay. A vertical translation shift literally is just going to take all of my values and shift them up or down based on what I have. So if I have an up to transformation, no, my asymptote should never change on a vertical translation. Okay. Technically, this dotted line is going on throughout all of the y values possible. Okay. It's going both up and down. It's basically canceling out any possible answer at those coordinates. So your vertical transformation isn't going to affect that dotted line. However, it will affect your x-intercept by shifting it up 2 units. Okay? And which would create a line that almost looks the same, is just shifted up by that value. In other words, it would look similar to this. If I erase the old line, there's my new tangent, shifted by up 2. Same thing over here. If I shift this value up 2, I get my new tangent graph that looks similar to this. Okay. And that's going to be the key thing with these problems moving forward. The big thing I want you to understand is that really when I deal with these graphs, number one, when I'm dealing with a cosecant or a secant graph, it's truthfully just sine and cosine. The same ideas that I would affect with those, I'm going to affect with cosecant and secant. I have a max and min change. I could have a period change. I could just move that physically left or right. The second thing I'm going to leave you on is always focus on the coordinates that are easiest to move. Your x-intercepts, your asymptotes, things that you know are at a set location that you can physically shift left, right, up, down to actually get to your specific coordinate that you're looking for, okay? If you try to focus on the coordinates that are strong decimals or very difficult to find, you're going to put yourself in almost a more challenging problem than it can be, okay? We'll be talking about the rest of these in class. Besides that, have a great day, and I'll see you tomorrow.